Okay, this is section 4.2, logarithmic functions. Most of the time we just call them logs for short, log functions. So what is a log function? What is a logarithmic function? In short, one way to describe a logarithmic function is it's the inverse function of an exponential, which is why this goes so hand in hand with section 4.1. If you remember, when we did inverses, how we would find an inverse is we would take the x and y's and we would switch them, which is switching the domain and range, and then we would solve for y. So for example, if we have something like f of x equals, and we're going to write down an exponential function here, f of x equals b to the x. This is what we talked about in section 4.1. b is the base, x is the exponent. If we were to try and solve this for its inverse, well, we would change f of x to y, and then we would switch the x and the y. Whoops, switch the x and the y. And then the question becomes, well, now how do I solve that for y? Well, this is kind of what the whole idea is of a log function, is in order for us to solve this for y, we have to come up with another way of writing this y value. We have to come up with another way of saying, okay, what is that exponent? How can I rewrite this so I can solve this thing for y? So we gotta, that's our exponent. We gotta come up with another way of doing that. Well, a log literally is an exponent. We're going to come up with another way to write y. So here's what we're going to write. We're going to say that y is equivalent to the log of x base b. And that's how we say it. That b is like a subscript of the log. The log itself is an operator. It's telling us to do something to the x. So this is the log of x base b. You might actually hear it said the log base b of x. The base is always the subscript. It's not in line with the x. So we are going to take the log of x base b. That's y. Okay, so a couple of things here. When you do this, x must be greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. And hopefully I will explain that to you in a way that you'll hopefully understand why that is the case. And it's going to relate back to the exponential function that we started with. Also, the base b has to be greater than 0, but b cannot be 1. And if that looks familiar, and I hope that it does, that's because that's the exact same criteria that we had when we had a function right here, the exponential function b to the x. B had to be greater than 0. Also, b cannot equal 1. Okay, and the reason for that is, now that we know how exponentials work, if I were to take 0 as the base, and I were to raise 0 to any power, 0 raised to any power is going to give me 0. Well, that doesn't change. That means the y value is always 0. It's never going to change. If I was to take 1 and raise it to any power, 1 times itself any number of times is still 1. Because 1 times 1 times 1 times 1, it's still 1. So those two values, 0 and 1, do not follow exponential patterns in which something will grow very, very fast or it will decay very, very fast. One of the two does not follow those patterns. So b being 0 and 1 are the only bases that are that you can't use other than negatives. Negatives don't work either because those do not follow exponential patterns. Okay, back to the logs in this case. The y equals log of x base b is another way of writing the exponent. As you can see, or as you should be able to see, this and this are the same variable. So logs are exponents. I'm actually going to write that. I'm going to write that in blue here. Logs are exponents. It is just another way of writing exponents. So Just if you can keep that in your mind as we go through this, it's going to make things a lot easier. If you understand logs are another way of writing exponents. Very, very important concept. Now, how are we going to go about changing between logs and exponentials? Because really what we have here is that this log of x base b is exactly the same thing. These are identical to b to the y equaling x. There should be an arrow there. This is exactly the same thing. Log of x base b and b to the y equals x are exactly the same statements. Okay, so how are we going to actually go about doing that? That's what we're going to do here in just a second. Okay, in our first example here, we're going to take and we're going to change a few different equations that start off as log equations. We're going to change those into exponentials. And then when we do another example, we're actually going to go the other way. We're going to take exponentials and change them into logs. But again, the main thing is you have to understand what the main pieces are. And we'll walk through that as we go. So our first one here, we're going to do the equation 2 equals the log base 5 of x, or the log of x base 5. Now remember, the idea was that the pieces really match up. And this is where you really have to understand that a log is an exponent. Okay, so if I'm going to change this into an exponential, I need some kind of a variable to equal my exponential. Well, the base here of the log, the base is 5. That's how you read it. This is log of x base 5. Well, the base of the log is exactly the same thing as the base of the exponential. So 5 is the base of my exponential. Remember that a log, again, equals an exponent. A log is an exponent. So this whole log of x base 5 equals 2, which means that 2 itself is the exponent because a log is or equals an exponent. So when I write this, 2 becomes my exponent. So it's 5 to the second power. And then what I'm taking the log of, and this is the only thing I really didn't define in the other piece, what I'm taking the log of, we actually call this the argument. It's what you are actually doing, the operation of taking the log of. That is what this will equal. So it's always going to be, and this is probably the easiest way to do it, I see this pattern written a lot, is people take the base of the log, you raise it to the answer over here, and that gives you the argument. So it's kind of a little loop pattern there. It's the base raised to the exponent of 2 equals the argument x. And we have now written this in exponential form. X equals 5 to the second power. Now we can obviously simplify 5 to the second power. That's 25. And if you can simplify it, go ahead and do so if it calls for it in the problem. Letter B, let's try it again. So now we're going to have 3 equals the log of 64 base b. So now the base is the variable here. It's not something that we have a value of, but it's still the same idea. Okay, and again, we're just rewriting it. We're not really trying to solve for anything here. So what we would do is we would take the base of b, raise it to the third power, and then that'll equal 64. So I'm going to write this as b to the third power equals 64. And again, if we were trying to solve this, we could probably figure out the value of b here. This is not something that I am extremely concerned with here. But again, that's how you would rewrite it. All right, let's try one more. Letter C. And now we're going to have the log of 7 base 3 equals y. And again, all we're trying to do is rewrite this in exponential form. So we're going to take 3 to the y equals 7. 3 to the y equals 7. Base to the exponent equals the argument. So the base was 3, exponent is y because a log is an exponent, so the log itself equals the exponent y, and then that equals the argument 7. And we have rewritten all three of the logs in exponential form. In the next example, we're going to come back and we're going to do it the other way around.